last lecture, we have modeled heat conduction in a nuclear rod. And we have seen that the model that we have developed that turns out to be Poisson's equation. The nature of Poisson's equation is that del 2 U equals F, and that is what we have seen. Now our goal is to solve Poisson equation numerically. This is a very important equation in physics and engineering, but only in very few cases such equation can be solved analytically. So numerical solution is the key. Also, this is a notorious solution. It takes long time to solve this solution in many cases. To developing an effective solver of Poisson's equation is very useful in engineering. The first step of solving Poisson equation is of course the discretization of Poisson equation. Once we discretize, we'll see that it will give rise to a system of linear equation. And we already know how to solve linear equations. So this is where you see that how linear algebra and calculus are coming together to solve a problem of practical interest. So a Poisson equation in general of this form, that is Laplacian of certain unknown, in this case u, is equal to f, which is a function of x, y and u in a 2D Cartesian case. Such equation we call Laplace equation when this f equals 0. This is another useful equation in engineering as well as in applied physics. Laplace and Poisson, they work together. Laplace was Poisson's student, and each of them they developed one equation that still we are using for various practical purpose. Typical boundary condition, as we have discussed in last lecture, there are three types. One is this Dirichlet, where specified u. Second one is Neumann, where this u prime or derivative of u is specified. And third one is Rabin, where this u prime plus au equals b. This kind of condition will come with a and b to be constant. In case of heat conduction, Dirichlet condition means specified temperature, Neumann condition means specified heat flux, and in special case it could be insulated or symmetric when heat flux is 0. Rabin condition come as convective condition, and in special case when convective heat transfer coefficient is very very high, then it will give rise to Dirichlet type condition. So now let us see that how we can discretize this equation. To discretize this equation, we take a domain, and this domain, let us say it goes from x 0 to Lx and y 0 to Ly. I start from x equal to 0 to x equal to Ls, and all these blue points I index it in x direction. I goes from 1 to nx. Similarly, in y direction, I starts from y equals 0 to y equals Ly, and the index goes from j equals 1 to j equals ny. Further, for simplicity, we assume uniform grid, which means this delta x and delta y, we can just calculate this total length divided by number of divisions. This delta x and delta y are uniform. They may not be equal to each other, but they are uniform, which means this delta x, what we see here, this is same at all points. Similarly, delta y is same at all points as I go in y direction. Now we see these colored points, and this is what we are interested about. I want to find out what would be the expression of u in this center point. And center point has several neighbors. It has two green neighbors, which is I minus 1j and I plus 1j when the center is ij. And then the red neighbors, which is ij minus 1, ij plus 1. So now I discretize this equation, and as I discretize, you know that this first derivative, this del 2u del x2, this will be the derivative, double derivative in these 3 points. We have this second order accurate scheme, we already know that is u I minus 1 minus twice uij plus ui plus 1 j. So this based on this 3 point itself divided by delta x square. Similarly, this del 2 u del y2, it will come as ui j minus 1, means this point just below our point of interest. This point itself uij, that is the center point itself, and then uij plus 1, that is what is above this ij, is equal to, in general, fij, because this f can vary from point to point. Of course, this nuclear rod problem, this becomes minus 1, but in general it can vary. Now you see this equation. In this equation we have basically 5 terms: ij, I minus 1j, I plus 1j, ij minus 1, ij plus 1. So this is an equation of 5 unknown. I can write the coefficients as a and aij minus 1, uij minus 1, ai minus 1j, ui minus 1j, aij, uij, ai plus 1j, ui plus 1j, aij plus 1, uij plus 1, and fij. So what are these a's? Well, first of all, this is applicable in all interior points between I2 to nx minus 1, means from here to here, and j2 to ny minus 1, means here to here. So this discretized equation that we have just developed, they are applicable in all the interior points, but not at the boundary. At the boundary, we must bring the boundary conditions, but let us not talk about that now. We have to establish something for the boundary, but this is applicable only at the interior point. Here this aij minus 1 and j plus 1, they are coming from here. They are coefficients of ui j minus 1 and j plus 1. So those coefficients are 1 by delta y square. Similarly, ai minus 1j and ai plus 1j, they are coming from here. So those coefficients are 1 by delta x square. And thus, this aij is coming from both sides. So it is minus 2 by delta x square minus 2 by delta y square. So now you see that at least the PD, of course we didn't talk about the boundary conditions yet, but you have an idea what you are going to do. You can now see that the PD is transformed into a system of linear equation. But what kind of linear equation it is? Well, let's see what kind of linear equation. So this is our discretized form. This is a linear equation, and we will have for each point, each ij, we will have one such equation. So in every equation, we will have 5 unknowns. Now, what are my total unknowns? This u vector is my unknown vector. Now, what are my total unknowns? Okay, my unknown starts from here, although I didn't write the boundary condition yet, but we will write it. Our unknown starts from here. This is unknown 1, unknown 2, unknown 3, unknown 4, etc., up to unknown nx. Then again I come back and start from here. Unknown nx plus 1, nx plus 2, etc., nx plus nx. Then again I come back here. Twice nx plus 1, twice nx plus 2, etc., So all the points are my unknown. So here when I write those unknown, my u vector is the vector of that unknown. So my u vector actually starts from this point this is my 1, this is my 2, this is my 3. So it starts from this unknown 1, unknown 2, unknown 3, etc., etc. All the way it will go up to the final unknown over the top. Therefore, here the coefficients in my A matrix, they will be multiplied with this U vector to give me the equations. So now you see, let us say this, I'm interested about getting the equation of this. When I'll write the equation for this point, that equation is written here. This Aij, the coefficients of that Aij, that will come over here at the diagonal. My Aij is here in this U vector. Coefficient of Aij will come at the diagonal. Because I am going, the point is going like this. Point is going like this. So I am going this unknown, then this unknown, then this unknown, then this. So I have hit here Ij minus 1, Ij minus 1. Then I hit nothing, 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 nothing. All coefficients 0, 0, 0, 0. Then I hit again. So coefficient of Ij minus 1 is here. Then again lots of zeros. Then I minus 1j. Then the next one is ij. Then next one is I plus 1j. Then again 0, 0, 0, 0, 0 will come from here. 0, 0, 0. Then I hit ij plus 1. So I have in this particular row is giving me this particular equation. In this equation, every equation contains all the unknowns. So you remember our system of linear equations. So a11x1 plus a12x2, etc., etc., a1 and xn, let's say. One equation is equal to b1. So every equation contains all the unknown. Here also every equation contains all the unknown. But here you see that every equation doesn't contain all the unknown, only 5 unknown. Which means that every equation contains all the unknown, but only 5 coefficients are non-zeros. All other coefficients are zeros. That is why we don't see those unknowns. So these a's are the coefficients here. a11, a12, etc. are the coefficients here. And all these a's are non-zero only for 5. And you can see that they will place over here plenty of zeros on this side. Then 0 in between. Then 3 points here, like this part is like our shape of our tridiagonal matrix, but then again lots of zeros and then 1 point. So this is something we call pentadiagonal matrix. Along this black dotted line, we'll get only non-zeros, but everything else in this matrix will be zeros. So overall, this matrix is actually very large matrix. This is an m by m matrix. And what is m? M contains all the unknown. If I have n unknowns, then I have a matrix of n by n, like the standard linear equation solver. Here, let us say I have this m by m matrix. M is the number of unknown. How many unknowns? Well, all these points are my unknown. Therefore, my unknown is nx multiplied by ny. That means this matrix size is m by n, which is nx multiplied by ny, then again multiplied by nx ny. So nx ny by nx multiplied by nx ny size matrix it is. So it's a very large matrix. If my nx is 10, the matrix goes 100. So it goes up very quickly. However, the good thing about this matrix is it has plenty of zeros. It has full of zeros. How many zeros? Well, it has at least, you can see that it has only 5 diagonals which are non-zero. So at max, you will get 5m number of non-zeros. So m square minus 5m will be zeros. Greater than that will be zeros. So plenty of zeros. So let us take an example here. So let's say that I have this nx and ny at 20. I am taking a very modest number. That means my total number of unknowns will be 400. So then my A matrix is 400 by 400, which means that its number of elements will be 400 squared, that is 16,000. So we'll have 16,000 A's in this A matrix. However, among this, we'll have only 5m, that is 5 into 400, 2000, maximum 2000. It will not be 2000, it will be less than that, of non-zeros. Remaining will be zeros, which means about 10% non-zero and 90% zero. So this matrix is very large, but then it is mostly zero, very few non-zero terms. And that is the good thing. That is what will help us to solve this matrix. Otherwise, this kind of large matrix, if they are completely dense, plenty of non-zero terms, mostly non-zero terms or all non-zero terms, they are not very easy to solve. But we are lucky enough to have something we call sparse matrix. So now this large sparse pentadiagonal matrix AU equals B, and we have to do something to solve it. First of all, this Thomas algorithm that we have developed before, in one-dimensional case, that will not work anymore because this is not tridiagonal. Well, there are some, we can play around with it and we can make Thomas algorithm work, but that's a different process, different discussion, and we will not discuss in that course. But in general, Thomas algorithm is not a good idea here. Other methods such as this Gaussian elimination type direct methods are not efficient because in large matrix, Gaussian elimination takes long time, number one. Number two is that Gaussian elimination type method will not preserve zeros. They will make these zeros non-zeros, then again non-zero, they will make zero. So it will require a lot of computation. Computer takes long time when they calculate with non-zeros as compared to calculation with zeros. So it's a good practice, if you have zeros, you preserve that zero during calculation. Therefore, we need a method that will solve AU equals B, but will not change the matrix U. And we know that kind of methods. They are iterative methods. They will preserve zero. And in case of large matrices, iterative methods usually require less calculation and consequently less CPU time compared to direct methods. That is why in problems like this, iterative methods are more useful. Now, Poisson solver is a huge challenge in numerical method. Poisson solvers, there are many Poisson solvers which will work, but Poisson solvers are usually slow, especially depending on Neumann or Rabin type boundary condition, it can become very slow. So we will not go the nitty-gritties of Poisson solver too much. There are many fast Poisson solvers available also. Here, what we'll do, we'll use the Gauss-Seidel method. We already learned Gauss-Seidel method. And we'll use that and we'll solve this problem using what we have learned in this course, that is Gauss-Seidel method. Gauss-Seidel method is the very efficient method for Poisson solution, and lots of solvers they use it. Most commercial solvers available, they have a Gauss-Seidel option. So we'll try that in solving our nuclear rod problem. So the summary of this lecture is that we have discretized the Poisson equation, discussed the nature of A matrix. We see the matrix A is large and pentadiagonal. And because it is pentadiagonal large matrix, it has to be sparse. So it is sparse. And now we are going to solve it. So before we solve, you go back to the linear algebra part of this course and review Gauss-Seidel method, because we are going to use that now in a computer program. So that's all for this lecture. Thank you, and I'll see you in next class.